get started. So we have the second talk by Sarah Pennington on Brownian bees.
Okay. Yeah. So thanks for coming back to the second lecture. Can you see my mouse when I move it around? Yeah, great.
Yes.
So just to recap what we talked about in the first lecture. So we talked about a branching selection system called the N-particle branching Brownian motion, or NBBM. And the particle system consists of N particles that move around on the real line according to independent Brownian motions, and they branch into two particles at rate 1. And when a particle in the system branches, then the leftmost particle in the system is killed. So there are exactly N particles in the system at all times. And the main result that we talked about was that if you take the NBBM particle configuration at a time t and you let n go to infinity, then the density of particles converges to the solution U of a PDE called a free boundary problem at time t. And this is what's called a hydrodynamic limit result. And it was due to De Masi, Ferrari, Brizzuti, and Soprano-Loto. And the sort of key idea of the proof was to sandwich the NBBM on a short time interval 0 up to delta between two different processes that are easier to control, that are based on branching Brownian motions. So in a branching Brownian motion, the particles just move according to Brownian motions, and they branch into two particles at rate 1. So in the NBBM, then each time a particle branches, then the leftmost particle in the system is killed. But what you can do instead is take a branching Brownian motion and then just kill particles at the end of the time interval, so that you start with N particles. So at the end of the time interval, you have more than N particles, but then you kill the leftmost particles at the end of the time interval, so that you end up with just N particles. Or what you could alternatively do is kill some of the N particles at time 0, and then run your branching Brownian motion starting with those particles. And with high probability, you won't have more than N particles at time delta. And it turns out that the NBBM is in a sense dominated by this BBM, where you kill the leftmost particles at the end of the time interval, in the sense that you can pair up particles from each process and have a BBM particle to the right of each NBBM particle. And in the same way, with high probability, the NBBM dominates this BBM. So you've sort of got a sandwiching for your NBBM. And in a sense, the reason that this works is that in this process, then you're sort of picking your winners at the end of the time interval, picking the ones that are furthest right. Whereas in this process, you're trying to pick your winners at the start of the time interval, so you don't do quite so well. And the NBBM is somewhere between those two. And then once you've got this result, then because the descendants of different particles in the BBM behave independently, it's much easier to control these two particle systems than the original NBBM. So that was the hydrodynamic limit result. And then I talked at the end of the lecture about a conjecture that said, roughly speaking, that the long-term behavior of the NBBM for large N should be roughly the same as the long-term behavior of solutions of free boundary problem. So today I'm going to talk about another particle system called Brownian bees, in which we can actually prove the equivalent of this conjecture. So this is the Brownian bees particle system. So this is a particle system in RD for an arbitrary positive integer d. So we've got N particles that are moving around in RD according to independent d-dimensional Brownian motions. And each particle is carrying a clock that has an independent exponentially distributed amount of time on it with rate 1. And at the end of that time, when the clock rings, then that particle branches into two particles. But each time a particle in the system branches, then the particle in the system that's furthest from the origin in terms of Euclidean distance is killed. So that means that we always have exactly N particles in the system at all times. So on the right, I'm going to show you what the Brownian bees might look like if we were if we had d equals 2 and n equals 4. So this is the origin. So the particles move around according to independent two-dimensional Brownian motions until one of them decides to branch. So maybe this green one. And then we see which particle is furthest from the origin. So that would be this one. That particle is killed. And then the green particle branches into 2 particles. And these 2 particles continue to move according to Brownian motions. So we still have exactly 4 particles in the system. And as I said, it turns out that it's going to turn out that we can determine the long-term behavior of the Brownian bees for large n through a connection with a free boundary problem. So a bit of notation, I'm going to write xn of t for the vector of particle positions of the Brownian bees at time t. So these are all positions in RD. So the positions will be x1n of t up to xnn of t. And I'm going to write mnt for the maximum for I in 1 up to n of the L2 norm of xin of t. So I'm always going to write this norm to mean Euclidean or L2 norm. And so mnt is the maximum particle distance from the origin at time t. So something that you might want to try and think about is what might be the limiting behavior of mnt if t and n are really large. So if we take the long-term limit of mnt, and then we take n to be extremely large, then what's the limiting behavior? So you might initially think that, well, because there are going to be more and more particles, then maybe this limit is infinite. But equally, you might think, well, because more and more particles means more branching, and so more killing the one furthest from the origin, then maybe they will end up getting sort of squashed near the origin. But maybe there's these 2 things balance out, and maybe it converges to a constant. So maybe have a guess and see whether you end up being right. So that's the Brownian bees. So now this is the free boundary problem that's going to turn out to be related. So someone is asking, so what makes this different from the NBBM? Yeah, so it's both the definite dimension and the killing condition. So even if this was in 1 dimension, then it would be different because we're killing the one that's furthest from the origin rather than killing the leftmost one, which is what we did in the NBBM. So the free boundary problem that's related to the Brownian bees is this one. So we'll take a probability measure mu0 on RD, and then we've got a pair of unknowns u and r. So u is a function of t and x, where t is a time and x is in RD. And then r just depends on t, and it's an unknown moving boundary. And we want them to satisfy this system of equations. So if you start away from no, well, if you start to the left of 0 in d = 1, then it would look like the NBBM for a while. Well, yes, that's true. So if you started a long way to the left, then it would. We are in ID, yes, but we could take d = 1, we could take d = 15. Okay, so we want them to solve these equations. So we want u to satisfy this PDE in the open ball of radius RT. And then we want u to satisfy a boundary condition. So we want it to be 0 on the boundary of the ball and also outside the ball. And we want the integral of u at time t over the ball to always be equal to 1. And then we want the initial condition at time 0 to be the probability measure mu0 in a suitable sense. So on the right, I'm trying to sort of illustrate this. So maybe this radius would be r at some time t, and then the solution u would be 0 on the boundary of this ball and outside the ball, and it would satisfy the PDE inside the ball, and the integral of u inside the ball would be equal to 1. So it's not obvious that the solution of these this system of equations exists, but it turns out that for any Borel probability measure mu0 on RD, so mu0 could have some nice density, but it could also just be a point mass at the origin, for example, then there's a unique solution u and r to this system of equations. And I'm going to call this system of equations FBP2. And also it turns out that RT is continuous in T for positive T. So we're always going to write BR of X to be the ball in RD with center X and radius R. So it turns out that for very large n, we can think of U of T and X as being roughly the density of particles in the Brownian bees at location X and at time T. So what I mean by that is that we look at the number of particles in a small ball, so with a small radius delta, center X at time T, and divide that by the volume of the ball and divide by n. And RT should be roughly the largest particle distance from the origin in the Brownian bees at time T, which we're calling MNT. So if we take these as sort of definitions for U and R, then why do we get this system of equations? Well, first of all, for the first equation, so if we take an X inside the open ball of radius RT, so RT is roughly MNT. And so if you're in this region, then you're closer to the origin than the largest particle distance from the origin. So particles are, at least for a short time, they're not going to be killed. So they're just going to happily move according to Brownian motions, and they're going to branch into two particles at rate 1. So that means that if U is the density of particles, then du by dt should have a smoothing term of half Laplacian U that comes from the motion according to Brownian motion, and then a plus U because each particle is adding a new particle at its position at rate 1. And then for the second equation, if we're at distance RT, which is roughly MNT from the origin, then particles that are furthest from the origin are being killed. So particles are being killed at that radius. And so the density of particles should be 0. So we should have U of T and X being 0 there. So that's the second equation. And then for the third equation, the total number of particles in our system is always equal to n. So if we give each particle a mass 1 over n, then the total mass of particles will be 1. So if we integrate the density at time t, then that should be the total mass, which is equal to 1. So that's the third equation. And then the fourth equation is just an initial condition. So that's a sort of non-rigorous explanation of a connection between the free boundary problem and the Brownian bees. So again, we can give a rigorous hydrodynamic limit result. So here's the hydrodynamic limit result. So we need a little bit more notation. We're going to write mu n of t and dx for the empirical measure of the particles in the Brownian bees at time t. So we'll have 1 over n times the sum from k equals 1 to n, and we'll put a point mass at the position of the kth particle at time t. So then what we can prove is, so if mu naught is a Borel probability measure on RD, and let's suppose that our initial particle locations at time 0 are IID with distribution mu naught, and let's let U and R be the solution of our free boundary problem with initial condition mu naught. Then what we can show is that if we take a time t and a measurable subset A of RD, then almost surely mu n of t and A, which is 1 over n times the number of particles in the set A at time t, so the proportion of particles in the set A at time t, that converges almost surely to the integral of U at time t over the set A. And MNT converges, so the largest particle distance from the origin, converges almost surely as n goes to infinity to RT, the position of the free boundary at time t. So I'm summarizing that in the boxes at the bottom of the slide. So the empirical measure of the Brownian bees at time t converges in some sense as n tends to infinity to the solution of the free boundary problem at time t, because this is essentially saying that the density of particles at time t converges to U at time t. So that tells us that if we fix a time t and we let n go to infinity, then we know what the Brownian bees look like. But now what we'd like to understand is if we fix a large n and we let t go to infinity, what's the long-term behavior of the Brownian bees? So for a large n. And so maybe a good first step would be first to understand the long-term behavior of solutions of the free boundary problem. And it turns out that solutions of the free boundary problem converge to a steady state solution. So we're going to have two unknowns, capital U and R infinity, that we want to solve this system of equations. So capital U is a function of x in Rd, and R infinity is just an unknown constant. And we want them to solve these equations. So we want U to solve a PDE inside the open ball of radius R infinity. And also we want U to be strictly positive there. And we want U to be 0 on the boundary of the ball. And we want the integral of U over the ball to be equal to 1. So it turns out that there's a unique choice of R infinity such that these first three equations have a solution. And for that choice of R infinity, then the choice of capital U is unique up to a scaling factor. And then the last equation tells you what that scaling factor has to be. And you can also see, if you compare this to the free boundary problem, that this capital U and R infinity is a steady state, a constant in time solution of the free boundary problem. And it turns out that all solutions of the free boundary problem converge to this steady state solution. So we can show that for any initial Borel probability measure mu0, then the solution U and R of the free boundary problem converges to this steady state solution, in the sense that the limit as t goes to infinity of RT is R infinity. So the position of the moving free boundary converges to the steady state free boundary. And also if we take the difference between U at time t and capital U and take the L infinity norm, that goes to 0 as t goes to infinity. So I'm summarizing that in the boxes on the right, that solutions of the free boundary problem converge as t goes to infinity. So there's a couple of questions. So yes, R infinity is finite. For d equals 1, there's an explicit value that's something to do with pi, and I can't remember what it is, what factor of pi it is. But yeah, it is always finite. Someone is saying no, so you don't require it to have bounded support. So it's kind of nice. So RT becomes finite immediately, but you can have an initial probability measure that has unbounded support, and that just means that RT, the position of the free boundary, goes to infinity as t goes to 0. But it's immediately finite, which is maybe slightly surprising. But so that's what happens to the solutions of the free boundary problem. So now let's go back to the particle system. So if we fix a number of particles n and we let t go to infinity, then it turns out that the Brownian bees converge to a stationary distribution. So we can show that the process xn of t has a unique invariant measure that we'll call pi n, which is a probability measure on Rd to the n. And for any initial particle configuration, the law of xn of t converges in total variation norm to pi n as t goes to infinity. So in particular, that implies that if you take a measurable subset C of Rd to the n, then the probability that xnt is in C, so the probability that the Brownian bees particle configuration at time t is in the set C, converges to pi n of C as t goes to infinity. So I'm summarizing that in the boxes on the left. So now a natural question to ask is, as n tends to infinity, then does this stationary distribution pi n converge in some sense to the steady state solution of the free boundary problem? Or in other words, is the long-term behavior of the particle system for large n the same as the long-term behavior of solutions of the free boundary problem? And the answer is yes. So this is what we can show. So if you take let's take a small positive epsilon and a measurable subset A of Rd. And then let's take the pi n measure of the set of particle configurations in Rd to the n, such that the proportion of particles that are in the set A is more than epsilon away from the integral of capital U over the set A, then the pi n measure of that set goes to 0 as n goes to infinity. And also if we take the pi n measure of the set of particle configurations in Rd to the n, such that the maximum distance of a particle from the origin is more than epsilon away from R infinity, the pi n measure of that set also goes to 0 as n goes to infinity. So what this means is that if we take a very large n and we take a particle configuration x1 up to xn in Rd to the n with law pi n, then with high probability the proportion of particles that are in the set A is very close to the integral of capital U over the set A, or in other words, the density is close to capital U. And also the maximum particle distance from the origin is very close to R infinity. So that's one way of sort of saying what the long-term behavior of the Brownian bees is for large n. But I also want to show you a slightly different way of stating it, which is also the main intermediate result in proving this result. So we need one more piece of notation. So for a configuration x in Rd to the n, we're going to write p subscript x to mean that the probability conditional on xn of 0, the initial particle configuration being equal to x. And I'm just reminding you of the notation for the empirical measure that's mu n of t in dx. So someone is asking, do we have stability result? So I mean, any initial condition, it converges to the steady state. We have some control over how quickly it gets close to the steady state. That's actually something that I will mention in the next lecture. Does that sort of answer your question? So this is the result I wanted to state. So let's take a positive constant k that we'll think of as being very large, and another positive constant c that we'll think of as small. Then if we take a small positive epsilon, then there are constants n epsilon and t epsilon, such that if n is at least n epsilon, and so if the number of particles in the Brownian bees is at least n epsilon, and if time t is at least t epsilon, then if we take a particle configuration x in Rd to the n, and we want it to satisfy a condition, so we want the sum from I equals 1 up to n of the indicator that the ith entry of x is in the ball of radius k, we want that sum to be at least c times n, or in other words, we want the number of, if this was a particle configuration, we want the number of particles that are in the ball of radius k to be at least this little constant c times n. And if we take a measurable subset A of Rd, then conditioning on taking x to be our initial particle configuration, then the probability that the difference between mu n of t and a, so the proportion of particles in the set A at time t, and the integral of capital U over the set A, the probability that that difference is bigger than epsilon is less than epsilon, and the probability that mnt, the largest particle distance from the origin, is more than epsilon away from R infinity is also less than epsilon. So if we're thinking of epsilon as being very small, then this is saying that roughly that the particle density at time t is roughly capital U, and the largest particle distance from the origin is roughly R infinity. So in some ways this is maybe easier to understand than the previous result, because this is sort of holding for any n bigger than this n epsilon and any time t bigger than t epsilon. But we do really need this condition here on x. So that's because if you didn't have this condition, so this is saying that at least a little proportion c of particles are within a big ball of radius k around the origin. And if you didn't have something like this, then you could start with all of your particles a really, really long way from the origin, and then you wouldn't have any control over the time that it might take for them to get back to the origin. So if you want to have something that holds for any times bigger than some t epsilon, then you need something along the lines of this condition. But so this is another way of saying that if n is large and time t is large, then the density of particles is roughly capital U, and the largest particle distance from the origin is roughly r infinity. So these are the results that I wanted to tell you about. And so now the plan is to, I'm first going to tell you about something about the proof of the hydrodynamic limit result. That's going to take up the rest of this lecture. And then tomorrow I'm going to tell you a bit about the proofs of the long-term behavior of the free boundary problem, and also a bit about the proofs of this result before I then talk about some different branching selection systems. So first of all, for the proof of the hydrodynamic limit. So what we're going to think about first is, rather than thinking about the locations of the particles in RD, we're going to just think about the distances of the particles from the origin. So we're going to let Fn of t and r be mu n of t and the ball of radius r centered at the origin. So that's the same thing as 1 over n times the number of I in 1 up to n, such that the L2 norm of xi n of t is less than r, so the proportion of particles that are in the ball of radius r. So it's going to turn out that Fn of t and r is closely related to solutions of this one-dimensional free boundary problem. So let's suppose that we have a function v naught from 0 infinity to 0, 1, which is measurable. And we've got a pair of unknowns, v and r. So v is a function of t and r. T is a time and r is a radius. And r is just a function of t, so it's an unknown moving boundary. And we want them to solve this system of equations. So we want v to solve a PDE for r between 0 and RT. And then we want v to satisfy two boundary conditions at RT. So we want v to be equal to 1 at RT, and we want dv by dr to be 0 at RT. And then we want v to be equal to 0 at 0. And we want the initial condition to be our function v naught. So at the bottom, I'm drawing you a picture of what v might look like at some positive time t. So usually we're going to be thinking of the initial condition v naught as being non-decreasing, in which case v will always be non-decreasing. And there'll be some positive rt where v is equal to 1 at rt and its derivative is equal to 0, and v is 0 at 0. And it turns out that if n is large, then we can think of v of t and r as being roughly fn of t and r. And we can think of rt as being roughly mnt, the largest distance of a particle from the origin. So why do we end up with this system of equations? Well, for the first equation, if we're at distance less than RT from the origin, then particles are closer to the origin than the furthest particle distance. They're not being killed. So they're moving around according to Brownian motions and branching at rate 1. And so for d equals 1, then we get a half Laplacian v from the movement according to Brownian motions, and we get plus v from the branching. And then for general d, we get this extra term in the middle. And essentially this comes from the fact that the distances of particles from the origin are not Brownian motions, they're Bessel processes, and they have a drift away from the origin, which is essentially just because if the Brownian motion is picking a random direction to move in, then it's more likely to be moving away from the origin than towards the origin. And that effect is stronger the closer you are to the origin. And so you end up with this extra term in the middle because of that. And then the second equation is just saying that the proportion of particles within distance RT of the origin is equal to 1, but we're thinking that all the particles should be within distance roughly RT of the origin. And then the third equation follows because the particles are being killed at roughly radius RT, and so the density of particles there should be 0, and that means that dv by dr should be 0. And then the fourth equation is just saying that the proportion of particles within distance 0 of the origin should be 0, and the fifth equation is just an initial condition. So again, it's not obvious that a solution exists, but we can show that for any measurable V0, then there exists a unique solution V and R to this free boundary problem. And there's also a natural connection between solutions to this free boundary problem and the previous d-dimensional free boundary problem. So if mu0 was the initial condition for our, well, if mu0 is a probability measure on RD, let's let V0 of R be mu0 of the ball of radius R centered at the origin. Then if we let V and R solve this free boundary problem with initial condition V0, and if we let U and R tilde solve our original free boundary problem with initial condition mu0, then it turns out that for a positive time t and a non-negative R, then RT is equal to R tilde t, or in other words, the free boundaries in each solution are the same. And also V of t and R is equal to the integral over the ball of radius R of U at time t. And this is what we would expect because we're thinking of V of t and R as being the proportion of particles in the Brownian bees within distance R of the origin. And we're thinking of U of t and X as being the density of particles at X at time t. So V of t and R should be the integral of the density over the ball of radius R. And we're choosing the right initial condition because we're saying that initially the proportion of particles within distance R of the origin is mu0 of the ball of radius R. So this is going to be useful later. So then it turns out that we can show an equivalent to, or we can show that this holds rigorously. So it'll be a sort of one-dimensional hydrodynamic limit result. Just reminding you of the notation that for xn a vector in Rd to the n, then we write p subscript xn to mean that we're conditioning on our initial particle configuration as being this vector xn. And then this is our one-dimensional hydrodynamic limit result. So we can show that there's a positive constant C1 such that if we take n sufficiently large, then if we take a time t, and if we take an initial particle configuration xn in Rd to the n, then let's let Vn and Rn solve our one-dimensional free boundary problem with initial condition given by V0 of R is Fn of 0 and R, so the proportion of particles in the ball of radius R at time 0. So under Pxn, then V0 of R will just be 1 over n times the number of entries of xn that are in the ball of radius R. Then we can say that the probability, if we start our Brownian bees with the configuration xn, that the supremum over R of the difference between Fn of t and R and Vn of t and R, the probability that supremum is at least e to the 2t times n to the minus c1, the probability is at most e to the t times n to the minus 1 minus c1. So this is saying that if we fix our time t, then if n is extremely large, then this will be very small and this will be very small. So we're saying that with high probability, Fn at time t is very well approximated by a solution of the free boundary problem with an initial condition that depends on the configuration xn. And what's going to be important later on is that even though the Vn, so the initial condition of the free boundary problem solution, even though that is determined by xn, the bound on the probability and this bound here don't depend at all on the choice of xn. So for any initial condition, then that initial condition determines the solution of the free boundary problem, but it doesn't determine how close you know that you are to that solution. And the way that we prove this, I'm not really going to go into the proof, and that's because it's very similar to the proof that I showed you in the last lecture. So the way that you prove this is that you can sandwich the particle system given by the distances of particles from the origin in the Brownian bees between two processes which are easier to control. And those two processes are branching Brownian motions, or at least they're the distances of particles from the origin in the branching Brownian motions. And the whole proof is very similar to what I showed you in the last lecture. So what I'm going to show you instead is how we can use this one-dimensional result that's only about the distances of particles from the origin to then get our full d-dimensional hydrodynamic limit result. And so one thing that we're going to need is to use a coupling between our Brownian bees and a d-dimensional branching Brownian motion. So in this d-dimensional branching Brownian motion, particles are moving around in RD according to independent Brownian motions, and each particle is branching independently at rate 1. So we're going to write xi plus of t for I less than or equal to n plus t for the particle positions at time t in this d-dimensional branching Brownian motion. So n plus t will be the number of particles in the branching Brownian motion at time t, and then each particle will have a label in the integers 1 up to n plus t, and xi plus of t will be the position of the particle with label I at time t. And then for an s between 0 and t, and for an I less than or equal to n plus t, I'm going to write x plus subscript I comma t of s to mean the position of the time s ancestor of the particle with label I at time t. And then what we're going to do is we're going to couple the Brownian bees with a d-dimensional branching Brownian motion in a natural way. So first we're going to construct a branching Brownian motion, but then we're going to construct the Brownian bees as a sort of sub-particle system of the branching Brownian motion. So we'll start the branching Brownian motion with n particles, and then each time one of the particles in our sub-particle system that corresponds to the Brownian bees branches, then we'll remove the furthest particle that's still surviving in the branching Brownian motion. So we'll remove the furthest particle from the origin, and we'll also remove all of its descendants. And that will mean that we'll get a Brownian bees system that will be a sub-process of the branching Brownian motion. And so for all times t, then so the set of particles in the Brownian bees, xn of t, I'm sort of abusing notation by writing this as a set instead of a vector. It'll be a subset of x plus of t. But also we can write xn of t, the particle locations in the Brownian bees, as the set of particle locations in the BBM at time t, where the location of their ancestor at all earlier times s was within distance mns of the origin. So this works because if any of the ancestors of the particle went more than this distance from the origin, then they can't have been in the Brownian bees, because this is the maximum distance from the origin in the Brownian bees. But it's not too hard to convince yourself that if this holds, then it actually means that the particle has managed to survive the killing off of particles furthest from the origin. So that's the coupling we're going to be using. So now I want to remind you of the assumptions for our d-dimensional hydrodynamic limit result. So we're supposing that mu naught is a Borel probability measure on RD, and that our particle locations at time 0 are IID with distribution given by mu naught. And we're letting U and R solve our d-dimensional free boundary problem with initial condition mu naught. And now I also want to say that V and R solves our one-dimensional free boundary problem with initial condition given by V naught of R is mu naught of the ball of radius R. So I said a couple of slides ago that if you take this initial condition for the one-dimensional free boundary problem, then the free boundary R that you get is the same as this free boundary R. So then this is going to be the main intermediate result in our proof of the hydrodynamic limit result. And it's essentially an upper bound on MNT, the largest particle distance from the origin, that holds uniformly over an interval. So it says that there exists a positive constant C2, such that if we take a small eta, then if n is large enough, then the probability that there's a time t in the interval eta up to capital T, such that mnt is bigger than rt plus eta, that probability is extremely small. Someone is asking, right, so someone is asking, why does that set of BBM points have exactly n particles? So it's not obvious that it does, but so MNS is the exact choice, which depends on the branching Brownian motion, such that this set always has exactly n particles. So I can't be explicit about what it is, but it is the exact barrier that, or it is a choice of barrier that yes, it's by the coupling, yes. Yep. So basically what we want, because this is actually not very easy to work with. So what we're going to want is kind of to replace this by something where particles are killed outside, something deterministic rather than this MNS. So that's kind of what we're working towards with this proposition, if that helps. So yeah, so for this proposition, it might look a bit odd that we have to take t from time eta up to capital T rather than from time 0. We have to do this because we don't have very good control over RT for very small values of t, but it turns out that this is enough for what we want. So what this is going to let us do is actually compare our Brownian Bs to a system in which a branching Brownian motion in which particles are killed outside a deterministic boundary. So I want to show you how we give you a sketch of how we prove this. So this is the first step in the proof. So it says that there's a positive constant C such that if n is large enough, then for a time t, then the probability that the L infinity norm of the difference between Fn at time t and V at time t is more than something very small, that probability is very small. So I'm now going to just sort of move things up the slide a bit. So I'm going to keep these things. So they've all just jumped up the slide. So these are our assumptions. This is the proposition we're trying to prove. And this is step 1. So how do we prove step 1? Well, let's let Vn and Rn solve our one-dimensional free boundary problem with initial condition given by V0n of R is Fn of 0 and R. So then we can just use the triangle inequality to say that the L infinity norm of the difference between Fn at time t and V at time t is at most the L infinity norm of the difference between Fn at time t and Vn at time t, and then plus the L infinity norm of the difference between Vn at time t and V at time t. And now we're going to bound both of these two things on the right-hand side separately. So for the first term on the right-hand side, we can just use our one-dimensional hydrodynamic limit result. So exactly what the hydrodynamic limit result said was that the probability that this thing is bigger than something very small, that probability is very small. So now for the second term, we can use that. So these are both solutions of the free boundary problem with different initial conditions. And it's not too hard to show that the L infinity norm of the difference between Vn at time t and V at time t is at most e to the t times the L infinity norm of the difference between the initial conditions. And then once you've got that, then so we can write down what this difference is. So it's the supremum over R of the difference between Fn at time 0 and R, and mu naught of the ball of radius R. But we're assuming that our initial particle locations are IID with distribution mu naught, and we're assuming that n is very large. So Fn of 0 and R is the proportion of particles in the ball of radius R. So with high probability, that's going to be very close to mu naught of the ball of radius R. And so what we use is something. So what you can use is something called a Glavenko-Cantelli theorem. Tells you that this is very small with high probability. So if you use a quantitative form of a Glavenko-Cantelli theorem, then you can get that this is likely to be extremely small. So that's roughly how we show step 1. And what we're actually going to use from step 1 is we're going to apply this with at position RT. So this tells us, if we plug in RT here, it tells us that Fn of t in RT is very close to V of t in RT with high probability. But by the definition of the free boundary problem, V of t in RT is equal to 1. That was one of our boundary conditions in the system of equations. So we've shown that Fn of t in RT is very close to 1 with high probability. So that was step 1. And then step 2 gives us an upper bound on Mn over a very small time interval. So we're going to let epsilon be n to the minus C3 over 2. And then we can show that if n is large enough, then for a time t less than or equal to capital T, then the probability that there exists an S in epsilon up to 2 epsilon, such that Mn t plus S is bigger than RT plus epsilon to the third, that probability is very small. So how do we show this? First of all, let's suppose that Fn of t and RT is at least 1 minus e to the 2t times n to the minus C3. So this is saying that the proportion of particles in the ball of radius RT is at least this. So by step 1, this happens with high probability, because so what we were saying up here is that step 1 implies that, so if we put RT in here, then V of t in RT is 1. And so the probability that F of t in RT is more than this away from 1 is very, very small. So let's suppose we have this. Then we can say that with high probability, 2 things happen. So we're going to use our coupling with the branching Brownian motion, just starting with the particles in the branching Brownian motion which have survived until time t. So the first thing is that we can show that by time t plus epsilon, the branching Brownian motion particles in the ball of radius RT at time t have more than n descendants in the branching Brownian motion. So that's because at time t, there were at least n times this particles in the ball of radius RT, just by the definition of Fn. And they've got time n to the minus C3 over 2 to branch, and they're all branching at rate 1. And this n to the minus C3 over 2 is much bigger than this little error here. And so that ends up meaning that with high probability, they've got more than n descendants because they've done enough branching. And then the other thing that we can show happens with high probability is that on a little time interval, so on the time interval t up to t plus 2 epsilon, none of the particles in the branching Brownian motion move more than a distance 1/3 times epsilon to the third from their time t ancestor's position. And the reason that we can show this is that on a time interval of length of order epsilon, then a typical particle is only going to move a distance about epsilon to the half. And so it's actually very unlikely that a particle, for a single particle to move this much bigger distance of epsilon to the third. And because epsilon is n to some negative power, and we're starting with n particles, then actually it turns out to be unlikely enough for a single particle to move more than this distance, that actually we can show that it's very unlikely that any particle moves more than that distance. So let's suppose that both of these 2 things happen for our branching Brownian motion. Then what that can tell us is that actually there has to be some S star in the interval 0 up to epsilon, such that Mn t plus S star is at most RT plus 1/3 epsilon to the third. So why is that true? Well, let's assume that it's not true for a contradiction. So let's suppose that Mn t plus S is bigger than RT plus 1/3 epsilon to the third for every S in the interval 0 up to epsilon. Well, what does that mean? Well, we've got these particles in our branching Brownian motion that start in the ball of radius RT, and none of them move more than distance 1/3 epsilon to the third by time t plus epsilon. So all of them are, if we have that in that time interval, so from time t up to t plus epsilon, Mn is at least RT plus 1/3 epsilon to the third. all of these particles are staying within that distance of the origin, so none of them are being killed. But there are more than n descendants of these particles, right? So this is giving us more than n particles which are managing to survive in the Brownian bees. And that's impossible because there are only n particles in the Brownian bees. So that gives us a contradiction and tells us that we must have this for some S star. And that means that at the time t plus S star, all the particles are within this distance of the origin. And then our second assumption here tells us actually that none of the particles from that time onwards move more than a distance 2/3 epsilon to the third from where they were at this time. And so that allows us to show actually that with high probability on the time interval t plus epsilon up to t plus 2 epsilon, mn is at most RT plus epsilon to the third, which is step 2. So that's a sort of rough explanation for how we get step 2. And once we've got step 2, we're in business, because now we can just apply step 2 with t equals k epsilon for each integer, non-negative integer k, for k less than or equal to t over epsilon. So we can just say that by step 2, actually the probability that that there's any k epsilon for k less than or equal to t over epsilon, such that one of these events happens with this choice of t, that probability is very small, just by a union bound. And so I mentioned before that RT is continuous for positive t, and that means that it's uniformly continuous on the time interval eta up to capital T. So that means that we can take n large enough that our little epsilon is small enough that rk epsilon plus epsilon to the third is at most rs plus this small constant eta for any integer k and for any s in this very small time interval after k epsilon, if s is in the interval eta t. So that means that if none of these events in step 2 happen for any of these t equal to k times epsilon for any of these k's, then that means that on one of these on any of these time intervals for s in any of these time intervals, then mn is at most this, which is at most rs plus eta, and that's what we wanted to show, that on the whole time interval mnt is at most rt plus eta. So that's roughly how we get this uniform upper bound on mn. So then it's actually fairly straightforward to, once we've got this, then we're really in business in terms of getting the d-dimensional hydrodynamic limit result. So this was our proposition, and then the d-dimensional hydrodynamic limit result is going to follow really easily from this claim. So the claim says that there's a positive constant C4, such that if we take a time t, a small positive delta, and a measurable subset A of Rd, then if we take n large enough, then the probability that mu n of t and A, so the proportion of particles in the set A at time t, minus the integral over the set A of u at time t, the probability that that's at least delta is at most n to the minus 1 minus C4. So I'll just show you how the hydrodynamic limit follows from that. So first of all, we have that mu n of t and A, so the proportion of particles in the set A at time t, well, that's just 1 minus the proportion of particles that are not in the set A. And also that we have that the integral of u at time t over the whole of Rd is equal to 1. So the integral over A is just 1 minus the integral over Rd minus A. So that means if we look at the probability that this thing is less than or equal to minus delta, then that you can work out that that's the same as the probability that mu n of t and Rd minus A minus the integral over Rd minus A of u at time t is greater than or equal to delta. And from the claim, you can get that if n is large enough, this is at most n to the minus 1 minus C4. So that means that we can put modulus signs in here and just add a factor of 2 in here. And because this is summable, that means that by Borel-Cantelli, almost surely for n large enough, then the modulus of the difference between mu n of t and A and the integral of u at time t over the set A is less than delta. And also that you can show that that implies that there's a delta primed, which can be arbitrarily small if delta is small enough, such that MNT is bigger than RT. And the proposition immediately gives us also an upper bound on MNT. So that means that almost surely as n goes to infinity, mu n of t and a converges to the integral of u over the set A at time t, and MNT converges to the position of the free boundary RT. So the last thing to do is to prove the claim, which won't take that long, but I think I actually might leave that to the next lecture because we've only got 4 minutes left. I mean, it's like a slide, but maybe it's better to do it next lecture than to rush it now. I don't.
Your call.
Okay. Okay, maybe I'll just do it quickly. Okay, so how do we prove the claim? So for a positive eta and a time t, let's let c, eta, and t be the set of particles in our branching Brownian motion at time t, where the position of their ancestor at all times s in eta up to t is less than or equal to rs plus eta. So this is the set of particles in a branching Brownian motion where particles are killed during the time interval eta up to t if they go outside this deterministic boundary. So then if MNS is less than or equal to RS plus eta for all S between eta and t, then that means that Xn of t, the particles in the Brownian Bs, are a subset of C eta t. So why is that? Well, if a particle so this is under our coupling with the branching Brownian motion, and if a particle in the branching Brownian motion is not in C eta t, that means that it had an ancestor which at some time during eta t was more than this distance from the origin, but that means that it was more than distance MNS from the origin, so it must actually already have been killed because it's further than the maximum particle distance in the Brownian Bs. So that means that mu n of t and a, the proportion of particles 1 over n times the number of particles in the set A at time t for the Brownian Bs, is at most 1 over n times the size of the intersection of C to t and a. So now that means that if we look at this probability that we wanted to bound, then we can use a union bound and say that if this happens, then either there's a time s in eta up to t where MNS is bigger than RS plus eta, or this doesn't happen, which means that this happens, which means that mu n of t and a is at most 1 over n times the size of C eta t intersect a. So that means that if mu n t and a minus the integral of u is more than delta, then 1 over n times the size of C eta t intersect a minus the integral of u must be more than delta. So now we're fine because so for this first term, we can just bound this probability immediately from this proposition up here. And then for the second term, so it turns out that if you look at the expectation of 1 over n times the number of particles in this C eta t, which are in the set A, then that actually converges to the integral over the set A of u at time t. That sort of comes out of properties of solutions of the free boundary problem. But also because the size of C eta t intersect A is, it's a sum of contributions from the descendants of each of the n particles at time 0. And each of those, so each of those particles, the descendants behave independently. And that means that you can get good control on the expectation of this quantity minus its expectation to the power of 4. And you can actually show that it's at most a constant times n to the minus 2. And so that means that with a sort of Chebyshev type inequality, you can show that this thing is very likely to be close to its expectation. And then its expectation, if eta is very small, is very close to the integral of u. And so this probability you can show is extremely small. So then this probability is small, which is what we wanted. So that's the end of the proof of the hydrodynamic limit result. So sort of the moral of the the proof was meant to be that in order to make progress, you need to be able to compare to a branching random motion where particles are killed outside a deterministic boundary. And once you've done that, then it's a lot easier to prove things. So I guess I should stop there. So thank you for listening.
Thank you. Yeah, so we have time for questions.
Is there, I mean, say you start with a point mass of X, and presumably you've got like a swarm that's going to slowly spread out and migrate towards the origin.
Yes.
Do you have any, do these results work to study the effective speed or dispersion of that swarm?
So I guess the speed would be given by the solution of the free boundary problem.
And do you have the speed in that case?
Yeah, I'm not. I mean, I guess it's going to be square root of 2, isn't it?
Will it?
Oh well, in one dimension anyway. Yeah, I'm not sure. That's a so I guess in one dimension, as Omar mentioned towards the beginning, then it would effectively be like an NBBM until some of the particles got near the origin. So I think in one dimension, it would have a speed, if n is very large, then it would have a speed about square root of 2. But then in higher dimensions, I'm not completely sure.
Okay.
But that certainly seems like something you should be able to get an answer to.
Yes, a question. So for the initial condition for these hydrodynamic limits, you take the particles to be IID with some measure, but is it not enough just that the initial configuration converges in distribution?
Yeah. So I guess the only place that it's used is yeah, back here, basically, that you need to have good control over this. So yes, I think as long as it converges in a suitable sense, then yes, that would be fine.
So you need slightly more than just convergence of the empirical distributions.
Well, you need the probability that this
yes.
supremum is
yes.
Yeah. So yeah, you don't need that much, I think.
So we will stop the streaming now.